Hey guys, welcome back. We're going to be looking at momentum a little bit more. The conservation of momentum idea is pretty easy. Basically, the momentum initial is going to equal the momentum final. So the idea here is that momentum is just transferred maybe from one thing to another in collision. And so we're going to look at the idea of how that works. And this is why if you run a car into a stationary object, all that momentum will then be transferred back into the car, and it can't go forward anymore. So all that energy has to be transferred back in the car, which crumples the car up, and unfortunately does damage to the person as well. Let's look at it kind of in some simple examples, and I think through these examples you can understand how this is going to work. If we had two railway cars of equal size. That doesn't quite look like equal size, and pardon my cold, but let's say that they ram into each other. Let's say that each of them weighs 3.0 times 10 to the fifth kilograms for each of them, and let's say that one of them is going 2.2 meters per second, and the other one is not moving at all. So they're going to collide, and let's say that there's no resistance on the railway thing, and this does not have a brake on it. So after they collide, you can imagine that then they will move in this direction, but because the mass is doubled, they're not going to move quite as fast. But so if the mass is doubled, if you have this mass here, but then they collide and the mass is doubled, what's that going to do to the momentum? Well, it's simply going to cut the momentum in half, because if you double the mass, if the momentum initial equals the momentum final, and momentum is mass times velocity equals mass times velocity. So we could write it out a little bit more specific. You could say the mass, let's say this is car A and this is car B. So the mass of A times the velocity of A initial plus the mass of B times the velocity of B initial is going to equal the mass of both of them. So we'll do AB times the velocity final. But you can see here that this is 0, right? Because the velocity here is going to be 0. And so really all you're doing is you're saying that the mass times the velocity equals mass times velocity. And since the amount of mass was doubled, it's just going to simply take your velocity in half like that. So the idea is that this always equals this. Let's do one that's a little bit more tricky, I suppose you could say. Let's say that we're going to be shooting at a target on ice patch. Let's say this is a freshly oiled ice patch. Okay. So we're going to shoot at a target, and so we have a high velocity bullet. And our bullet is going and it hits our target, and it goes right through our target. Okay, and so the target initially then had no velocity, of course. Let's say that the velocity of the bullet was 475 meters per second, and let's say that when the bullet left the target, it was going 275 meters per second. So what's happened is some of that momentum will have been transferred to the target, and since this is a freshly oiled ice patch, there's no resistance, and that means that this will then have a velocity. So how do we figure this one out? Well, same kind of thing. The momentum initial equals the momentum final. So what we want to do is we want to just break this up, kind of like I did over here, and then we'll just insert all the parts and pieces. Pretty simple, really. So the mass of the bullet initially times the velocity of the bullet initially plus the mass of the target initially times the velocity of the target initially is going to equal the mass of the bullet times the velocity of the bullet final, because they're not together. So these are just going to add together, right? So the momentum from this bullet initially is going to transfer some to the target, and since it keeps going, it's still got a good bit of a momentum itself. So then we also have the mass of the target times the velocity of the target final. So we only don't know this one variable, so pretty simple to do. All you're going to have to do is throw in your mass. So say you know that the that the bullet weighs 0.035 kilograms, and let's say that you know that the target weighs 2.5 kilograms. You're going to need to know that. So the mass of the bullet is 0.035. The velocity of bullet initial is 475. 75. Sorry about that handwriting. Plus 0, because this is going to be times 0, because initially it's 0. Equals the mass of the bullet, same thing, 0.035 times 275 plus, you got 2.5 here times your velocity final. So pretty simple. Multiply these together and multiply these together, subtract that and divide by that, and you'll end up with a velocity final equaling 2.8 meters per second is what I calculated. So that little target's going to be now moving after the bullet hits it at 2.8 meters per second. So this is pretty simple stuff. Let's go ahead and just do one more example. Let's say that you got an ice skater. Here she is. We'll make her a girl because they like to ice skate more, I think. And let's say that she's not only an ice skater, she likes to throw things. So let's say that she decides to throw a rock. And she's like mad. Maybe she's throwing a rock at some other kid on the ice skating patch. She's a naughty girl. All right, well, so there's no bump in the ice here. Let's say this is a flat, freshly oiled ice patch, right? And so it's just, just freshly oiled. So let's say that she is just standing there and she chucks this rock. So let's say that she weighs 39.85 kilograms, right? And let's say that the rock weighs 0.15 kilograms. It's a good sized rock. And let's say that she chucks that thing. She's really angry. So let's say that she chucks that thing at 55 meters per second. All right, and so what's going to happen? Well, the momentum initial is going to equal the momentum final. So initially, she's at 0, right? And the rock is at 0, okay? So initially, my momentum is 0, right? And so then my momentum final is going to be the rock flying this way, and she is going to have to move backwards. And so the momentum of her moving backwards has to equal the momentum of the rock flying that way, because the momentum final has to equal the momentum initial, and the momentum initial is 0. Let's go ahead and figure this out. So we've got 0.15 as the mass of the rock times its velocity is 55, right? Plus, let's see, plus the her mass, right, is 39.85. right? And the velocity final here. So if you go ahead and add this out, what you realize is that so this has to subtract from this because it has to equal 0. So you do the you do all the algebra here, and so you'll end up with finding out that the velocity final of that rock, or of her, is negative 0.207 meters per second. So she'll actually go backwards then at just 0.207 meters per second. So since it's a backwards direction, we define it as negative, and the rock is in the forwards direction. And this is the same reason why, when you shoot a gun, here's a gun right here. So the bullet goes out at a very high velocity, but you'll feel that the gun will then have a recoil. It'll push back on your hand, and that's this whole idea. Is like if your initial momentum of the gun is 0, your final is going to be something, but whatever the momentum backwards on the gun has to equal the actual momentum on the bullet. But since the bullet is so small in mass, and you plus the gun is such a high mass, that there's not a lot of backwards velocity, at least not more than you can handle. So or at least some people can handle. So this is kind of the idea of conservation of momentum, and this is real linear, just going backwards and forwards. So in the next one, we'll talk about what happens when things are hitting each other at angles, and then how do we figure out the conservation of momentum.